Okay, let's talk a little bit about the units of pressure. So we know that pressure is force over area, and so that tells us that the units of pressure, so square brackets again mean units of, would be the units of force, which is newtons, divided by the units of area, which is meters squared. And so there is a special symbol for that in physics. It's called the Pascal, abbreviated PA, like that. But people in research, people doing research, let's say in vacuum, relatively seldom actually use pascals. We almost always use other units, which makes life a little bit difficult, but not so bad. So 1 atmosphere of pressure, so the pressure that is surrounding us in the air right now, is 101,325 pascals. That's also 1.01325 bar. So you can see from this that 1 bar is equal to, 100,000 pascals. That's the definition of a bar, but it's about equal to an atmosphere as well. As we already said, it's 14.7 pounds per square inch. That, although I wrote it like this, usually it's abbreviated PSI, pounds per square inch. When you are dealing with a compressed gas cylinder, 1 atmosphere will register as 0 on that because it's measuring pressure relative to atmospheric pressure. So 1 atmosphere would be 0 psig, where the G here stands for gauge. But very often the pressure gauges are just marked in psi, and it's left for you to infer that it really means psig. And then finally, this is equal to 760 torr. So all these different kinds of units are commonly used in research for measuring pressure. So now we're going to use the physics that we know to derive a couple of really important fundamental relationships for fluid physics, and then we'll apply them to some examples. So we'll start by deriving the equation of continuity. And this is really just the statement of conservation of mass for the special case of an incompressible fluid. So when we say incompressible, we mean something where basically its volume doesn't change when you squeeze on it. And so most liquids can be approximated as incompressible. Really, when you squeeze on them, their volume does go down a little bit, but in many circumstances, it's a negligible amount. So let's consider the cross-section of a pipe with fluid flowing in it, or flowing through it. And this pipe is going to start out with a relatively large diameter and then neck down to a smaller diameter. And the fluid is flowing out from the left towards the right. So let's consider a cross-sectional plane that cuts through the pipe. So this is a plane of cross-sectional area A sub 1. And we are going to ask, in a time delta t, time interval delta t, what volume of fluid passes through that plane? What volume of fluid passes through this plane? And obviously that depends on how fast the fluid is flowing. So first, let's think about, given the speed, let's say that the speed within this pipe, let's say the fluid is flowing with a speed v1, then in the time delta t, the fluid moves a distance, we could call it maybe delta x1, which equals v1 times delta t. So I'm going to indicate that here, and maybe we'll shade this in blue. And so this distance is delta x1, which is v1 delta t. Now, if the fluid is incompressible, then let's consider a different plane in the next down region. So this is a plane of area A2, and during that same time, delta t, that time interval, or just during the time delta t, the blue volume of water, meaning the volume that I've shaded in blue here, has to pass through every plane perpendicular to the flow, and that would include this plane here. So whatever volume is passing past this plane during a time delta t must also pass through this plane, because we're talking about an incompressible fluid. So during time delta t, the blue volume of water must also pass through the plane with area A2, because the fluid is incompressible. So let's think about how big is that volume. So we will think of the pipe as having a circular cross-section, and so that means this blue volume is kind of a squat cylinder. So the volume, delta V, would be the cross-sectional area, which is A1, A1 times the height, which is delta x1, and I can rewrite that as A1 V1 delta t. Now, we're going to allow the possibility that the fluid is flowing at a different speed, V2, in the thinner part of the pipe. So that same volume that's shaded in blue in the fat part, it would occupy a longer length of the skinny part. So the same volume here would be delta V, but now instead of writing it in terms of the cross-sectional area of this plane, we got to use the cross-sectional area A2, and we're allowing the velocity to be different, but the time interval is the same, so it would be A2 V2 delta t. And so now we just have to equate these two expressions for the volume, the delta V. So equating, we get A1 V1 delta t equals A2 V2 delta t. And if we cancel the factors of delta t, that leaves us with our final result that A1 V1 equals A2 V2. And that's called the equation of continuity.